Hi everyone, this is David Adebi for Power Labs, and this is the Blue Couch podcast. Today we have a very important guest. I would say she's one of the pillars of Power Labs. I will allow her to introduce herself. But before we do that, I just want to ask a random question. What's the most counterintuitive thing you've learned about optimizing anything? Maybe energy systems, maybe any other thing. What's the most counterintuitive? You never expected?
I think how smart human-made heuristics already were. So you build big models and we try fancy things, and many times in real life, one operator in that lab has already decided that turning this on by 5 p.m. every day is the optimal choice, and somehow he was right.
So basically humans rock. Humans are cool.
And experience on domain experience is incredibly important.
Yeah, so those priors that we have could be maybe better than when something is just everything is learnable. But yeah, okay, that's cool. That's cool to know. I guess people like OpenAI, and the rest will not like this. They believe everything can be learned.
I mean, he also learned, right? It's nothing. He
learned.
He didn't make that decision.
Okay. That's, should I say 1-0 for biological neural networks? So yes, I would like our guest to introduce herself.
I'll just paraphrase David. My name is Eghonghon, and I'm one of the pillars of Power Labs, allegedly.
Eghonghon handles hardware and R&D at Power Labs. We are Power Labs. We are trying to push the boundaries or the frontiers of electricity across every layer. So what she does is really important to the, should I say, future and present of Power Labs. So to me, when people say optimization, I'm always like, okay, optimization. Yeah, everybody wants to optimize something, right? But it sounds like you are just fighting entropy. Are we really winning our fight with all these new compute, data? In fact, what is optimization? Because we were just talking about optimization. What is optimization? I don't even know what optimization is.
Wow.
What it is? What is it? Yeah, can you just give us should I say cliff notes of what optimization is, and in terms of for electricity or energy systems?
I mean, in general, the question that we ask is, given a finite set of choices, what is the best one to make? That's the high-level optimization goal, right?
So it's a finite set of choices.
Yes.
That's simple, but my own problem is sometimes that finite set can blow up sometimes.
But that's the problem. That's why we have jobs, right? It's finite, but it's a really large set. So we need smarter ways to simulate outcomes of choices and quickly decide which ones are worth exploring or not. Okay.
Because I sometimes I'll be like, okay, you want to optimize something, and that optimization is maybe is convex, so you're minimizing something, right?
We like that.
Yeah, we like. Sometimes you want to maximize something.
It's the same problem.
It's the same problem. Just turn it. Yeah, exactly. So let's say you're going to minimize the amount you are spending for electricity, say in this building, which is what Power Labs does. One of our products, Pi, does that. So we are able to do sizing optimization. We are able to do dispatch optimization. So say we want to do that, and we want to reduce the levelized cost of energy. Cool. We have a particular uptime that we are targeting. So that's a constraint. But sometimes, maybe because I was a scientist.
David is still a scientist.
So I used to be like, okay, you want to optimize this thing, but are you taking into consideration things that happen in real life? For example, if you give me a schedule and say, oh, this is the optimal time to have this level, this lower cost, right, for 8 hours a day. But am I taking into consideration something as stupid as maintenance?
Maintenance is very, very important.
You get if I leave this thing, hope this thing will not. So I guess that means the data that you're going to collect is a lot. You have to take into consideration the should I say physical assets that you're getting information from, how they are degrading.
Lifetime use, sequence-dependent maintenance. Read my paper, by the way, on sequence-dependent maintenance.
Yeah, that's interesting. So we are going to add to the show notes Eggie's paper on this. So that's interesting. So that means those constraints are getting bigger and more complex.
I think we come back to that popular saying we have in science, right? All models are incorrect, some of them are useful. There's the uncertainty set of what can happen in life is
so large.
It's incredibly large. So for us, it's where it becomes part art and part science.
Yeah, that's I like that. I like that. So there's an art to it.
There's an art to modeling, and it's also where I always really talk about domain expertise. Like artificial intelligence can do a lot for us, but we have to ask the right questions. So when I'm modeling my problem, what kind of maintenance should I consider? Which of my assets degrade at what rate? And are they important enough? If I'm building schedules on an 8-hour time slot size or whatever, and my generator only breaks down once in 10 years, at what level should I include generator degradation in my model? That's a design question, right? So you can also have hierarchical models even that optimize over different time scales and do this, because sometimes it just doesn't make sense now. Like, so how many 8-hour time slots will pass before that event happens that I should already keep it in mind now? Okay, these are different design choices. For some systems, you can choose to do that. It can be worth it that if it's 0.01% degradation every time I turn on the generator, and I know that based on the physics of this machine, I can include that in my model. If I don't know that at all, I can have like different models operating at different time scales that look at.
Okay, that way you have like this model is like more short term, this is more longer term.
So the longer term model takes output of the shorter term model as input in deciding what the long term trajectory of these systems are. That
makes sense. I like analogies a lot. Where you have like a neural network and you have maybe edge detectors that are tuned for a particular stuff.
Precisely.
Then you have something like a meta level that gets the output, and that's cool.
Because like you said, search space for each of these problems is already incredibly large. If many of them, if they were not NP hard, we just solve them by ourselves and go home most of the time.
I wish we just had like one formula, we just plug it in and crunch it out.
I mean, you could. Heuristics are always still an option.
Yeah.
So you could, if you come up with a really smart single formula that is like, I don't know, 90%.
So optimization is really about exploration, right?
A lot of it, intelligent exploration.
Yeah. So one question I'm like, okay, for to optimize, you are spending compute.
Yes.
Right, and we don't have infinite compute, right? And maybe time also, we don't have all the time in the world. So is there like a perfect optimization solution? I've always felt, sometimes perfect is when you do perturbation, right? At the end of the day, you have to stop somewhere, like when this is good enough. Ignore the other thing. Mathematicians used to make one joke about physicists that for like Taylor series, you just care about the first two. And like, I beg.
And just so that when you get to engineers, you reduce the number of terms you care about.
Exactly. But mathematicians, they care about all the ends, I beg. Yeah. So I'm like, are we always trading accuracy for speed? I need to get this answer. So the question is, how do I know the answer is good enough? You alluded to the fact that, if you have domain expertise, you kind of have a sense of what makes sense, right? Like this answer is good enough for the system. But if you don't really have domain expertise, you are just crunching numbers, you might not know when to stop.
So mathematically, optimal means something. There's a fixed definition for it, right? So if I have a clearly defined objective function, I know when I have hit like I cannot get a better solution than this.
Okay.
There's a mathematical definition by that. So when to stop is actually defined. When your model tells you optimality gap is 0%.
Yeah, but maybe you've not got to that. It's like it's going to take a long time. Sometimes you have like some functions are like, I don't know, they are like asymptotes. Like you're just,
of course. So we always stop somewhere. There's always some tolerance value.
Okay. So how do you pick that?
This is also an art. So many times when we make these models, I'm optimizing cost or something, right? So you are running a system. You used to spend 5 million before.
Okay.
And now you spend 2 million, but your optimality gap is 60%. As a mathematician, I want to keep pushing.
Okay.
But as somebody that has shaved his cost right now,
like this is good enough. Don't let me overdo it.
So while we can always do more, and in the science, I mean, that's our job, that's what we want
Yeah.
to do. I feel like practically we know what is good enough. As your stakeholder, your decision makers
Yeah.
know what value
In
is.
terms of time, your engineering
in terms
time.
of engineering time,
yeah.
in terms of what the outcome is. The other thing is we're always making assumptions within these models. No model is 100% accurate
Yeah.
representation of reality, right? So even if I claim 0%, it is based on the assumptions that I have.
Okay.
So while it's worth it scientifically to chase this
Goal of
this
perfect optimal.
in most practical cases, nobody cares.
Yeah.
Good enough is defined more by company KPIs or market metrics. That's where good enough comes from, and that's how we know when to stop.
I guess it's this school, should I say school boy or school girl idea that when you're in secondary school, people think things have like definite answers, but when you start doing your scientific research, you know that reality is not. So, for example, you learn equations of motions and physics, and you learn all those equations like you get it. But when you get to like maybe in university, you start saying that most of the things that you're going to be doing will be numeric analysis. So even send
differentiation.
Yeah, exactly. so most people that don't really go further, and they were very good with the maths and physics in high school. So they lead through life thinking that yes, they should have an answer, should have like a deterministic answer. But I'm sorry to tell you, it doesn't. Well, that makes it fun. So I guess when you talk about optimization, some people will be focused on the models, some people will be focused on how to even run those models, like the compute, So which area are you more interested in? I know what area I'm interested in. I'm interested in about the applications for now, but I suspect sometimes, even if you're interested in the application, sometimes you need to push the boundaries. That means you need to go. It's just like I'm sorry for using too many competing terms, but it's like you have to go and check the libraries, and sometimes you have to write the library yourself.
We would hope not. So we want this to be accessible.
Sometimes,
right? Things become necessary, but the hope is that we can make generalized interfaces.
Yeah.
That users can model and solve and go away. That would be nice, right? So it makes it more it increases adoption of these methods. So I was doing a doctorate before this, still kind of but most of that was focused on building solvers themselves, right? Reasoning within the solver.
That's so interesting. Why I say it's interesting is for we at Power Labs now, we are not trying to build solvers. Mm-hmm. We have problems we want to.
We will.
Yeah.
Eventually.
So exactly. So the eventually is when it's like a point where we feel we are not really getting enough, bang for our buck. Yes. So we feel okay, maybe we can push the envelope in this space a bit. And so I have one question. So when we push the envelope sometimes, maybe we create new methods. Are we looking at writing papers about these? Are we looking at maybe publishing open source tools about these? Not in the application per se, but in the underlying technology sometimes. I know that some people keep something as secrets, but I feel sometimes when you push the boundary of science a bit, of what the state of the art is. You might not do it that year. Supposedly Newton said he's able to see fire because he stood on the shoulder of giants. Although it was actually jabbing someone that was not very tall. Newton was a mean person. But so let me leave it at that. But my point is, that idea is true. Where some of the things we use are, we use some of these open source tools. I love to be at the point where, yes, we are leading in terms of the amount, we're capturing value from whatever it is we are doing. At the other end, we are also giving back in terms of, what the state of the art is, and, maybe it could be just from publishing. We don't have to share our code. We could just publish a paper, and so people don't waste their time, waste their computer. Oh, Eggy has solved one, big problem that,
a lot of pressure for Eggy.
So maybe you win I don't know what award you are going to win for. Maybe the field medal for solving one, who knows.
So reasonably, of course, we are still a profit-making entity. But sharing science is part of the goal.
Exactly.
R&D that's buried in a hole somewhere is not that.
It's not that useful.
Yeah.
And I think, when sometimes you stretch the capabilities when you put out something out there and other people are seeing it from other
Challenges
perspectives.
thoughts of the entire community, right? Yeah.
Like web is something that one guy was just doing in CERN. And right now we are going to post this on Spotify. You have to. So imagine CERN does not, CERN will publish it. Anyway, I really believe in sharing, but I really believe the devil is in the details. There could be, so I can publish a paper, someone can decide to use that paper, based on that paper, implement something. I might have implemented it, keep some, things for myself, because I feel that's where my moat is, right? However, I don't think we would be building what we are building without people having published. And people let me just put it this way. A lot of people just think, IP, let's just keep IP. I don't like sharing my opinions about some things that people want to patent sometimes. I remember when I was 22, I was trying to build a 3D printer. That was a long time ago. And then 3D printers were not like the way they were now. And there was one company, I think, I'm trying to remember their name, but they LDD, no, there is not, this is open, this public information. So they had the patent for 3D printing for like 20. They stifled growth in 3D printing until the patent expired. People outside, and people just made the technology way better than they could ever imagine.
Okay.
So yeah.
There are two demons within me.
Okay, let's
industry and academia, right? So
let's compare the two demons and see the one who will sell our soul to.
It's industry versus academia, and this is exactly the point. The logic, the reasoning is very different. If I publish a paper and I kept some things to myself, that's bad science, right? Good science should be reproducible. This is how we get peer review. Everybody should be able to reproduce those results, validate them, counter them. So if we say we are keeping some things to ourselves, we're already eroding the science.
I mean the application. So I don't mean the actual core idea. Like
sometimes it's not so easy to separate these two things, right?
Transformers is different from ChatGPT.
Yes.
So I will keep ideas about
ChatGPT
to myself, but I would have published a Transformers paper.
Yeah. That's
where my seat. Although I know I get you, it's not. Sometimes it's very, because sometimes to even show that the idea works, you need to actually do an application. So if you now start hiding it, it's not. Yeah, I get you.
But again, you are still a profit-making entity, right? If everybody can immediately reproduce your results.
Yeah.
I mean, there are other things that say what a successful product is or not, right?
So I think the problem is not just about the R&D, it's about being able to capture the value from your output. So sometimes people are able to create new technology, but they are not able to capture the value from it, and they maybe don't exist anymore. And you see it a lot in the industry. Why some people are so good at capturing value, maybe not so good at creating new technology. And so I think what we should to be at the middle, where we are able to capture value and also able to create. That's the ideal situation we should be in. But so okay, I'm also curious about some of the models, some of the algorithms, and so I would like you to assume I'm someone with a math degree and I have some Python skills, and I don't have money to go to Power Labs, because Power Labs is more should I say enterprise customers, and I'm reading your paper and you want to just teach me about optimization. So walk me through, say I'm trying to optimize my electricity bill at home versus an industrial plant. So what kind of models would I be looking at, and why should I be looking at those type of models?
We have many choices.
Yeah, but you said there's an art to it. So instead of looking at the entire universe of choices,
some of it to be preference
okay.
based.
Okay.
I am a huge fan of dynamic programming models.
Oh, interesting.
Personally, state transition.
Okay.
This happens, this goes to that, and I think for many people that are not super mathematically inclined, it's a logic that I have found this easiest to explain.
Okay.
To operators, to people, right? So that would be my first
way to go about it.
Yeah, make a dynamic programming model And these days in the optimization landscape, there are many conversion tools in between. People can build constraint programming models from your dynamic programming model. So with that, the tools that are available to you are actually quite generous.
Okay. So I don't know dynamic programming. I know I will just go online, Google, maybe see a tool. I don't know what that tool is. Then so basically it's like a converting. It's in a way you're like getting stills from a video.
Yes.
Yeah. Okay. I hope people got that.
There's also bigger things happening in this space actually. There's chatbot that I know of that allows you to describe your problem in just like LLMs are doing everything.
Yeah, prompting.
And then it tries to give you a model and say, okay, does this represent this problem you just described to me? It's still incredibly iterative, but it's a start for somebody that does not have modeling experience.
I think when you do some, so I don't know how. I think when I was, I'm trying to recall the problem that made me, mess with like when you start learning. Was I trying to apply for something then, maybe 2016? So one thing I just noticed then was dynamic optimization sounds like a fancy way of saying it's complicated. It's complicated. So like this is complicated. So, and you said like you preferred that, right? And I think that makes sense. Where when you think about it, even most models, like you said, all models are wrong. Some are useful. Even some, and I will now modify that a bit. Like all models are wrong. Some are wronger than others. Because the thing about it, like for example, in mechanics, we know that classical mechanics is like a particular. You can get classical mechanics from quantum mechanics, right? So, but what they teach you is like, so basically you have like an equation, and you know that if you just maybe assume some things for this equation, it turns that equation to what you are more familiar with, right? And the analogy of like having a video, you just get stills from that video. I think that makes sense, because when you start from something being that way, if things get complicated, as it will get, things will actually get complicated. It's very simple. We want something simple, but unfortunately, nature is not simple. It's an unfortunate reality. So I guess maybe that way you still have the, arsenal to tackle it as it gets more complicated. It gets more complicated. That's interesting. So, when you hear optimization, you hear about it a lot. Like even people that do machine learning, obviously they have optimizers.
Your training process.
Yeah, like gradient descent is basically optimizer. And people start coming up with, for example, I heard people came up with a better version of Adam, extending it to be better. And Adam has been there for a long time. People,
First man.
Exactly. Maybe that's why. So, but maybe people want, I don't know. People want something better than Adam.
I mean, we want to improve training, right? Training is already the most time-consuming, energy-consuming portion of
Exactly. People want to optimize that. It's interesting that machine learning is really about optimizing.
We optimize to learn, and then we learn to optimize.
Exactly. It's better.
Even within combinatorial optimization problems, a lot of times you are seeing machine learning aspects. This point of modeling, for instance, it's not always clear what my model is. I can learn my model from data.
Yeah.
For example, right? So it's a.
So, how do you model something as unpredictable as petrol prices in Nigeria? I'm just like, we are modeling things, but you have a constraint, and that constraint is one annoying constraint, because okay, I can figure out how much sunlight I'm going to get, I can figure out those ones, but the petrol price in Nigeria is very dependent on what Dangote says today and what another person is saying, NNPC. So it's basically it's stochastic.
Very stochastic. It's almost like weather predictions, right?
So we are weather.
I think Nigeria is even worse than the weather. Because
at least you can predict weather day by day. You still get day by day. You still get at least weather prediction is not bad. If you are looking just within today, tomorrow is when you are going far. It becomes more complicated. But I think in Nigeria sometimes it's even difficult. I could be driving back home this evening and I might just discover that there's fuel scarcity and petrol is now, I don't know. I hope not. I hope it will.
Now 1.5.
I just had to like, because it's insane that it's like almost 8x from about like a year ago. So that's interesting. So
Wow.
so can maths really tame things like that?
To some degree. So predictors are a learning problem, right?
Yeah.
And we almost never tell you that my next prediction is 100% accurate. There's always some kind of accuracy, I don't know, percentage. There's always some chance that your model is wrong. The question is how wrong. I hold the belief that in the limit of infinite time, everything repeats. There's actually a pattern to be learned, given that you have.
But we don't have infinite time.
We don't have infinite time.
It might be like another billion years before you get that exact pattern, because someone said if you give monkeys a typewriter, eventually they will come up with what's. Well, the problem is they didn't think about the infinite time. That means the monkey has to be Methuselah or not die, because.
Go back to the question of good enough.
Yeah, so maybe eventually the monkey types, you are beautiful. You can just say this monkey is new Shakespeare. That's good enough. You don't need to complete the entire thing. You're like, oh, monkey types Eureka. That's interesting.
There's also chances to build in some safeguards within your optimization models. Like we know that we are depending on predictors, and these predictors are not 100% accurate.
Yeah.
So there are methods to make your model a little more robust to inaccuracies of your predictor.
Okay.
We can do that within reasonable limit, of course. Like something like petrol just going 8 times is this huge outlier
and some of the problem is that some of the things that happen is like there's so much human element there that it's not like, okay, maybe you're able to even map out, maybe it's like there's a season that stuff happened.
Yeah.
It's just,
if you had a predictor that did that, you would actually throw the data point away.
yeah.
Your data engineer will look at it and say, it misbehaved.
Let's just ignore this guy.
Exactly. So even for us as people evaluating these
Yeah.
predictors, even when it's right, if it's right in a way that's completely outrageous.
Yeah. I want like a practical example. For example, give us a breakdown where an optimization algorithm saved money. Like maybe it could be a city, it could be like a building. For example, this building, we are actually optimizing. I guess maybe eventually we'll publish a case study about it. So can you give a break? Okay, you know what? A cliff notes, not go into too much details. We don't have the time, and I don't think maybe it's necessary to really.
There's a popular example of the Google Office, right, and their reduction in energy usage costs.
Yeah, like people talk about that, or well, Google never published.
It's science versus industry.
Because that was like that's actually interesting. I don't know to go into that too much, but that was DeepMind's first application, and people are like even the cost savings was maybe enough to pay for the amount they paid for DeepMind, because they basically optimized their data centers and they used less energy. Some people say almost as much as 40% reduction. That's massive. That's really massive. So yeah, that's like a good example.
But they also publish cases, especially these days with routing for these grocery delivery firms or companies that have been in the more developed world.
Yeah.
Travel time of your salesmen, or what are they called, delivery men,
I get
have also been significantly improved for many of these companies.
Yeah, but I'm concerned about electricity or energy is because those problems, I don't want to say they are more. Okay, so that problem you are trying to minimize time, so you want to get to that next location.
It's also cost, right? If you minimize time,
yeah. So obviously less time, less fuel you're going to be spending, and also
less salary you're paying.
You're paying the people out, they'll do more work. So
the
thing is, for a big for like a well planned city, right, is easy to, even when you let's say you're not even optimizing, you can estimate how long am I going to get to location X. But if you live, say you're living in Ikorodu, you're going to VI, so it's you don't know. Let me get on the road first. it becomes more annoying, So I think it's the same kind of problem anyway, whether you're packing stuff, whether you're trying to get to a location. I just suspect that electricity has so much variability in terms of the data you're getting from, especially when it comes to the cost of some of your like the inputs. A lot of geopolitics affect that.
Yes.
Unlike some other things. So yeah, and also another problem is the usage. So sometimes, I know you might like eventually like the usage is not static. It's also dynamic. People are changing how they are using. Yeah, you can see seasonality in your data, but sometimes, how would someone would not have predicted COVID in January 2020?
Okay.
Energy optimization.
First, I would say that in general, demand patterns are actually very predictable.
Yeah.
Human beings as a group, individually we're different, but as a group we're incredibly predictable human beings. At 6 o'clock, all of you wake up and on your lights and draw from a group.
I like this example because there is a study that discovered, I think in the UK, there's a particular show they watch and they saw a massive spike. So apparently people during the break they go and make tea.
Exactly. So as a group, we're very predictable. Demand is not the big question. Of course, anomalies like COVID happen, and suddenly all of you are working from home, and daytime demand changes a lot. But with dealing with anomalies, for instance, let's remove the Nigerian context.
Let's be general.
Yeah, that stresses me out. But let's say generally, I am optimizing on a day-to-day basis.
Yeah.
Anomaly happens one day in 10 years.
Yeah.
That day, my model is very wrong, but all the rest of the time, my model has saved me. So cumulatively, we're actually still largely correct. So what we want to do is to mitigate the effects of when we are wrong. This is what the safeguards are. I don't want you to die the one time I'm wrong. It's doing worst case time versus average case time, right, of this kind of thing. So that's the kind of reasoning that we do once we leave the purely mathematical landscape and start dealing with real world problems.
So I want you to give our users something, should I say, that they will like listen to this. I said our users, not just Power Labs users or Pi users, listeners. So people are just listening now. Maybe you are not like a big company and maybe you learn something from what Eggy will give today. So is there something that is not very obvious and turned out to be like a brilliant energy saving solution? It was not obvious, like maybe you are optimizing some. Okay, so let me give an example. In terms of you talked about roads, for example. You are trying to deliver something, right? It might not be obvious to say, oh, maybe you should just build or pass. Maybe you should take these roads. Maybe that road sound like maybe it didn't make sense to people. But when you discover that, the way the location is, okay, let me give an example. So let's assume I'm going to VI. And there are multiple locations to VI, but the main road everybody knows is this. But I discovered that, if I go and pass, if I take these routes, maybe there's a boat or whatever that will take me, and it's just 30 minutes, and I get to VI in like 40 minutes, rather than taking. I'm just creating one very unlikely scenario here. Yeah. But I mean something that is not like very obvious to people. And I really love looking at systems and seeing maybe their arbitrage opportunities, So sometimes it could be, okay, for example, in a building, hope I'm not giving the answer you want to give. In a building, I could discover that let me pump, if I have solar, let me pump water when there's sunlight rather than at night. Maybe at night would have been maybe more convenient, but I discovered that, if I actually pump my water during that time, like in the maybe 12 p.m. or 1 p.m., I'm seeing that I'm actually seeing serious savings. I'm not saying you're going to save, but I'm saying you might, right? So those kind of non-intuitive things, right? It will be intuitive to me eventually if I think about it clearly, but most people will not know that, the time that you decide to use something, for the grid too, it matters too. I guess maybe that's why in some other countries their tariff is based on time. Because they've seen how
based on demand.
The demand. Right? So I would decide to do something at when the cost is low. So is there anything that you just want to do this? Maybe there's one advice that people just use and maybe their bill. My last NEPA bill I hope my landlord is not listening. But my last NEPA bill was 105,000 or something. So yeah, band A. Yeah, I need band A. I need band A for the band A. So is there something that you can like maybe it's not obvious, and you can tell our users that based on your experience optimizing energy systems, that yeah they could do and they could see some cost savings. It doesn't have to be 20%, it doesn't have to be 50%, it could be as small as 2%.
As half a joke, turn off everything. Like if
So
you don't do anything, there's no cost. But a bit more seriously, I think the decision of, which is not always in users' control though, when to charge your battery
okay.
is actually like a significant thing. There's a lot of energy.
When to charge your battery, and when you mean battery, you mean like
so you have an
inverter system. Okay,
yes.
cool. Okay.
So
Cool.
intuition is every excess production of solar, just send it to storage for later.
Okay.
But I feel like this is not something so clear that somebody can immediately control. But there are moments where the actual best decision for you is not to charge at that time and just waste your power, kind of. There are some instances where that is the optimized decision to make.
Okay.
But this is not really advice for people. This is not something in their control. I'm trying to think of.
Okay, I would have said it's not in their control before, but now that there's band A thing, people have like almost 24 hours electricity.
Okay,
So they're trying to
if you're in
reduce.
band A and it's really expensive, it's sometimes not going to be worth it for you to charge your battery.
Yeah.
You can still meet your uptime that you need without spending that savings cost. Because I know it's the instinct, right? You want to tap it running, save it for next time.
Yeah, I think I agree with you, and I will tell you from my own. Okay, don't let me share that experience. I'll share it off camera. I talked to me about it. Yeah, you just discover that you're just drawing more power, you're racking more bills, and when you don't really need it because you have multiple sources available, and you know. So yeah, that's interesting. Well, we've touched a lot on optimization. I think I should start optimizing my life too.
Well, that's the question, right? What's the objective function? If you want to optimize your life,
I have too many objective functions. Multi-objective.
Multi-objective.
It's too much.
Is massive.
So one question: if we increase computing power tenfold, what kind of problems in energy optimization can we solve?
Well, I'm very interested in the same kind of problems, but increasing the timeline that we look at.
Okay.
That gives us larger arbitrage opportunities because we're able to kind of see the future, able to see into the future.
And it makes sense for our customers at Power Labs because many big businesses they plan ahead for a couple of years. So it's not just about next month. They can make 4-year plans, 3-year plans. That's actually cool.
Yeah. So because of compute right now, we do shorter time scales. But give me more power, I will plan over.
What is the most intriguing unsolved problem in energy optimization today? Is it something where traditional techniques or maths doesn't cut it? What's the most intriguing problem? Like, this is the problem that if I solve, I win my field medal.
Okay, I don't know about the field medal.
Or Turing or whatever. Or
like, I don't know that it's a core mathematical problem
okay,
or like an application-based kind of solution. Because I think there are lots of surprises, or maybe not surprises. You know when somebody predicts something, but the community doesn't take it that seriously.
Yeah.
So right now we deal with grid unreliability here.
Yes.
But these are also coming to developed nations with grid congestion.
Yeah.
So that's something that, if you say 10 years ago, the developer was not, at least most people, the people in the know, if you know, you know, kind of, right? But it's becoming more apparently a problem with this massive electrification that we're doing.
Yeah.
That even those grids are...
Basically, we're converting everything to electricity, cooking, even driving.
And that's a demand that we were not prepared for.
And now, the demand, before demand was very predictable. But when you add transportation, you are charging your EVs. Some people work at night, so people will charge different times.
Yes.
It just messes up the...
So these demand patterns that we have grown so used to, it's not the demand curve now. You've probably seen it.
Yeah.
I'm trying something in my hand.
It's a duck curve. It's usually like a duck curve.
But is it still that curve if I'm now charging my vehicle overnight in my house?
Okay, that's interesting.
So these kind of changes, and how do we, because changing grid infrastructure is a slow process.
Look, I was wrong. I said duck curve. That duck curve is for solar.
Yeah, actually. But you know that.
I know.
Dips and all this.
You have peaks and goals,
Yeah, but those peaks are changing with the electrification of almost everything that we are doing.
Yeah.
And how fast can you really change a national grid infrastructure? So I feel like this is where like optimization has a huge role to play for how we distribute these limited resources, which is what we are trying to do, right? If we had infinite resources, there's nothing to optimize. You just pump everything at it. But with these limited resources, limited infrastructure, how do we do that? Coupled with the issue of your renewables, right? We are electrifying and moving away from consistent kind of supply.
Okay, like gas is fairly consistent, nuclear, but now we are doing things like solar, wind. So
the combination of these two problems, I think, makes it very interesting for me that both developed and underdeveloped nations, from an optimization perspective, are faced with very similar challenges.
Converging now.
Exactly.
Maybe that will make the solution faster now. People want to solve it because you have the same
Rich
problems.
people problems get solved faster.
Faster because you see, tropical diseases, you spend time, people don't solve it. But if something like an illness that affects the whole world, the vaccine will come out very fast. That's interesting.
So this is my most intriguing optimization challenge in the energy space at this time. Next week, my mind may change. We'll settle into a pattern again. Okay. I don't think by the time we reach saturation, at some point we will have all the EVs that we will have in a population, and then we'll settle into some kind of pattern. I don't know what it will look like compared to the current curves that we have.
I'm looking at it from the electrical engineering point of view also, the fact that the battery tech is going to improve so much and there will be embedded battery across. So I suspect the grid will not be the way the grid was in the 20, 30, 40 years ago. People think you just build more powerful grid. I think what was going to happen is there's always going to be storage embedded across. So people can, those, should I say microgrids or smaller places can always, they can, how do I put it? Everybody has a spinning reserve, distributed spinning reserve, let me call it that way. So I think we'll get there, but even if you have batteries, you still need to optimize, right? So if you're adding battery, that's you need to optimize, okay, I have batteries. And interesting fun fact, I worked on a project that's similar where they have what they call demand response programs in Canada. And there are times when they try to make people use storage from their batteries, right? So basically, you are using the storage in your batteries, maybe at peak period. So that actually makes sense. So, we were mentioning the fact that maybe you should not charge. So imagine you've charged already. Then you're getting to a point where electricity is more expensive at a peak period. Then it makes sense to use what you've saved, right? Then you use that. Then when you leave the peak period, you get to the low cost tariff. Then you can start charging back. So that was interesting, and I think it's not going to be something that is just maybe Canada, Norway. It's going to be something that will be across the world going forward. I don't think I have any questions that you are just answering all my questions. So I don't know, maybe you have questions for me, but I think it's nice just talking about optimization and how it's a core thing that we do here. We have a tool. I know everybody know about Pi already. If you don't know about Pi, you should know about Pi. You know about Pi. It's not meat pie and it's not chicken pie. This is Pi, and it's an amazing tool that is going to make all these maths concepts more practical for businesses. At the end of the day, it's really about how do I shave 5, 10, 15% of my operating costs. So just check out the link to Pi and you can get started. So Eggy, do you have final words for our listeners, for me, for everyone here?
Stay jiggy, man.
Okay, you've been told to stay jiggy, conserve your, I don't know about conserving. I think optimize, use energy abundance with optimization.
Optimize joy also.
Optimize joy, yeah, that's interesting, yeah. So it's nice to have you here, and hopeful we would have another episode with Eghonghon, maybe definitely in 2025. So stay tuned. We'll discuss more boring, cool stuff. All right.
Thanks.
And that's the end of the Blue Couch podcast. Although, let me tell you one secret: we are not sitting on blue couches today. So
this is a black chair.
Yeah. So it's a shade to someone. Anyway, bye.